Thank you very much, Andrew. Good morning, everyone. Normally, when I come up and give a talk, I talk about the fractures and large-scale reservoir simulation, and I want to talk about something slightly differently today, which is much of blue sky research, a little bit more longer-term vision. It's a research project that started because of foundation CMG or energy simulation, not necessarily because of the funding, but because of the people that we have met, the colleagues that we have met. Yesterday, Eric sort of praised Rick for providing this great pointer here. I have now to praise Rick for actually a lot of really insightful scientific discussions around 3D printing, which allowed us to, in collaboration with Rick, to set up this project, share some ideas, his trust in showing us your trade secrets. And we have now a really nice project around 3D printing, which complements very nicely some of the work that Rick is doing, and occupy some of this white space between his chair and our chair. So why do we worry about pore-scale physics? Fundamentally, if you look at reservoir-scale processes, it doesn't really matter if you're interested in IOR or EOR or geothermal reservoir. The process, the large-scale reservoir behavior is determined by the physio-chemical processes that happen at the scale of the pore, so how the fluids interact with each other and how the fluids interact with the rock. And what has really revolutionized our understanding over the last 10 years is that we have fast X-ray CT imaging, which allows us to peek into the pore space and see how the fluids displace each other and how the fluids interact with the rock. And so, for example, a few years ago, we published a paper. This is a big pore, about a millimeter-sized pore in a carbonate rock, and the red stuff is trapped oil. The pore is water wet, and as you change the capillary number, as you change ever so slightly the injection rate, suddenly this big trapped oil blob shatters, it's broken up into little droplets, and starts to move again. So we've done, and these are things that you've never seen before, or you didn't even hypothesize before the advent of CT imaging. Hannah Menke, who was a postdoc who recently joined our group, she did some fantastic work on imaging reactive flow at the pore scale. So yesterday, some of our colleagues Leonardo talked about wormhole formation. So she created, using fast 4D synchrotron imaging, unique data sets that show how the rocks dissolve in real time, under which conditions, carbonates, for example, you have compacted solution fronts, you get wormholing. Now, this is all great. There's a fundamental issue, is that's a lack of repeatability of these experiments. So when we set out this experiment here above, we didn't know at the start of the experiments that these big pores were water wet, or Hannah didn't know how reactive individual grains in that carbonate sample were. So if you want to redo the experiment and say, well, what would happen if this big pore or these big pores were oil wet, it's really difficult to design lab experiments that have a priori, pretty much impossible to design lab experiments that have a priori known properties. So this is where digital rock physics or pore-scale modeling helps us, because it complements the experiments. It allows us to upscale some of the small-scale physics to the continuum scale and add value to these very complex data. So you could run a simulation and say, well, what would happen in that instance, pore-scale simulation, if these pores are now oil wet, not water wet. But again, there's some problems. The moment we go to some of these more complex displacement physics, some of fluid-rock interactions, a lot of these pore-scale models are not properly validated. And I'm going to show you some examples where they start to fall down. And what we think, and this is sort of the long-term vision that was inspired by Rick, is that 3D printing could eventually enable us to do fully controlled, repeatable experiments. We print a piece of rock, we know exactly what its wettability, its reactivity, its pore size distribution is. So you can do repeatable experiments and can use the experimental data to understand, to advance our numerical simulations. Different pore-scale modeling techniques, and some people get really excited about arguing one is better than the other. I have a much more pragmatic approach. Things like pore network modeling, where you approximate your pore network by essentially sticks and balls. You have idealized transport routes, they're computationally efficient. But if you have more complex physics, you need to think how you put these complex physics into the pore network model. Lattice-Boltzmann methods are very popular. You model fluid flow as a propagation collision of particles. Computationally expensive, but trivial to parallelize, so there's good scalability. Again, the issue is how you convert Navier-Stokes to the Boltzmann equations. If you have complex physics, wettability changes, etc., it's difficult to add. What we do is we're going to talk about a little bit direct numerical simulations where we directly solve mass balance. It's very adaptable to new physics, but it's computationally expensive. So use these direct numerical simulations to understand some of the small-scale physics and then enrich the larger-scale pore network models. Arne showed yesterday how you can use these pore network models, for example, to get insights into polymer flooding. What's the industry relevance? There are a lot of companies these days who say, well, give me a piece of core, I scan your core at different resolutions, I extract a digital rock, I extract the network, I run some simulation, I get your petrophysical properties, and you stuck them in the reservoir simulator, and off you go. Now, there are a lot of steps in how you analyze your data, how you pre-process your data, how you set up your pore network simulation, your pore-scale simulation. This doesn't replace scale experiment. There's some companies who pretend it would replace scale experiments. I'm very critical. I think it's a very, very powerful tool to enrich scale experiments, to understand how fluids displace each other, but it's nothing that, at the end of the day, replaces good old laboratory work. Because at the end of the day, it's a simulation exercise, you need to validate your simulations. So what you would normally do is you do some lab experiments, you get your relevance, for example, and then you run your pore-scale modeling and you tune parameters until your lab experiments, these dots here for two-phase flow, even three-phase flow, match the predictions or match the outcome from your simulations. And Arne and Consorbi from Heriot-Watt University, they wrote a paper a few years ago and say about 16 to 20 different parameters and more parameters in that matching exercise than you have in your traditional history matching exercise. Or even if you want to forecast the evolution, I think, of the universe, there are less parameters to do a model than what we need to match use pore-scale modeling to match experimental data. Again, it's a really powerful tool if it is used right. Now, interestingly, there is now a movement to say, how can we do some very clever small-scale micromodel experiments to validate our pore network or pore-scale simulations? And there was a study done by MIT a couple of years ago. They used some silicon-based polymers to create micromodels, so these little pore structures, to do lab experiments of two-phase flow. They had a little inlet port where they injected some fluids, and that it had a non-wetting and a wetting phase that displaced each other. What they worked out is that if you use these PDMS-based macromodels, you cure them in UV light and you can change the wettability. So there's this fantastically rich data set where they look at anything from strong imbibition to strong drainage at different flow rates and capillary numbers to see how two fluid phases displace each other. And they released that data set earlier this year or late last year into a benchmark study and invited companies and research institutions from across the world to say, here's the data set, throw your best simulation tools at it, see how well you can model it. 14 different participants, some from industry, a lot from academia, participated in this benchmarking study. We did this as well in our group. We're sort of on the right here. Interesting, some of the professional service companies who deliver, we promise you, we predict pore network modeling-based rel perms from your CT scans didn't participate in that work. And generally what you see is there's some instances where, here's the experimental data, where the different simulation tools really nicely capture, at least qualitative, in sort of a semi-quantitative way, what the lab experiments do. But there are also instances in the bottom row where you're far off, whereas clearly some of the physics in the pore network models and the pore-scale simulations are missing. Some of the tools work straight out of the box for the cases where you match experimental data nicely. Others require quite a bit of tuning. So it's a fantastically open access benchmarking study that really harvests the power of international collaboration. Before I talk a little bit about what we think we can do better with 3D printing to improve that validation of pore-scale models, I want to talk you quickly through our approach of how we do some of our simulations. So we do direct numerical simulations, which means we solve the Navier-Stokes equation for two-phase flow at the pore scale using volume of fluid method. We track the interface between two fluids by an indicator function. So blue is one fluid phase, white is another fluid phase. So in your grid blocks, you label it 0 as the fluid phase is the blue fluid phase is absent, 1 it's present. The interesting bit is what happens if you're somewhere here in the middle where the interface crosses one grid block. A couple of challenges. You need to maintain a sharp interface. You need to reconstruct it. Because we have capillary force, we have surface tension, we need to avoid that you have any spurious oscillation at these surface tension, because if you don't do this, your results are going to be very much off. Here's a little experiment here at the bottom. So these are 2 fluids of equal density. One has, so initially set up as a square, so capillary forces, surface tension forces should change that square box into a round ball. On the right-hand side, you see the evolution of the velocity at this interface between the red and the blue fluid phase. You see the ball forms, but you have these numerical instabilities at numerical precision, and they eventually, like the wing of a butterfly, cause chaotic behavior, and this bubble starts to move. So there's a lot of clever mathematics going in how you handle these spurious oscillation. Another problem is time stepping. So these are computationally really intensive simulations. You need to think about how you parallelize things, etc. So the nice thing about using this direct numerical simulation approach is you can add a lot of physics very easily. So it's quite, what we want to do is we want to add component transport in the 2 different fluid phases so that we can model how one fluid phase reacts with the rock with how the other fluid phase reacts with the rock, or the 2 fluid phases react chemically with each other. For example, during EOR, during CCUS, geothermal applications, how these 2 fluid phases interact chemically with each other, how they may change, for example, wettability. Again, quite a bit of very clever mathematics needs to be done. How you track the fluids at this interface, the standard approaches, the continuous species transport approach that is published in the literature. What happens is that you get some numerical dispersion of the chemical components across the fluid-fluid interface, which is non-physical in many applications. We rework this, so we have now a different approach where we really track the interface between 2 chemical components exactly, so that the reactions really only happen within a given fluid phase, and you don't have chemical reactions that are somewhere dispersed across that interface. It doesn't matter at the reservoir scale, but if you try to understand what's happening at the pore scale, you need to get these physical processes, these chemical processes modeled correctly. Again, what we now have is a really nice tool where you can take some thin sections of rock samples, you have some grains, you have some pore space, and you can model the displacement of 2 different fluid phases. The 2 fluid phases react with each other. It can change the wettability. We can add some polymers if we want to. It's quite a flexible approach to model. The fluids can snap off, they can coalesce, they can form bubbles, etc. It's quite a powerful tool to understand some of these more complex pore scale displacement processes. And we strongly believe in reproducible science, so everything is open source. You can download, you can just go to the web, you download it. It's based on open foam. We claim it's the world's first and only DNS code capable of fully coupled multi-phase reactive flow simulations, including surface complications, including wettability. We've applied it, and I'm not going to go through all these pictures, I can show you later. We've applied it to a number of little studies, from low salinity flooding to calcite precipitation to calcite dissolution to snap-off and pore geometries, etc. And wherever we had some experimental data, we compared it and validated and benchmarked against published experimental data. And just go through this because it takes a little bit of time. So how can we do better? Where do we want to go with this? So how do you get from simulation to 3D printing? Our vision is for this project, of this long-term research, is that we 3D print little micro models of a pore space. We know exactly what the pore space geometry is. We know exactly, eventually we will know exactly what the reactivity of the pore space is. We know what the wettability of the pore space is. We visualize first in 2D, later in 3D, the displacement processes using a clever setup on your top left. And then we complement this with our simulation tool and see how well, and we can quantitatively exactly compare how well do the experiments on the left, the rich data set, compare to the simulations on the right. Now, to do the 3D printing, we have bought a little 3D printer. Essentially, it's a resin printer that has a certain resolution. And if you go to Alexander's poster later on, he's going to explain to you exactly how we tune that printer. So we do that. We have this little in-house printer to do some very quick experiments. But again, we're working with the RIX team and other commercial vendors to get other samples printed and see actually how well does the printing technology work to print these high-resolution micromodels that we want to have for flow simulations. Why is that? Why do we need to do this homework? A lot of papers now occurring in the literature say, we've 3D printed a micromodel, we've done some fantastic experiments, here you go, great science. Think, hold on, not so fast, my friend. We do look at the print, because no one really looks at the printing quality. If you actually ask people and say, have you looked at the quality of your 3D printed micromodels? Well, you got them commercially and believe they're of good quality. So here are some examples. We took, this is a grainstone of a carbonate, we 3D printed this little micromodel, and then we put it into an SEM scan. We see sometimes the 3D printer blocks flow path, sometimes you have sort of feathering, permeability at the grains that you have 3D printed. You have some low resolutions, you have all these small-scale artifacts in 3D printing. Why do we worry about them? If you look at two-phase flow, and we look at more complex processes, such as imbibition and drainage, where your contact angle varies and you have hysteresis, you really need to control what is happening at the surface with 3D printed grains if you want to go to reproducible lab experiments. The challenge is around meshing the geometry and actually linking the simulations to what you see in the laboratory, because you need to resolve the pore space geometry accurately. If you do this, you very quickly end up with millions and millions of cells, and your simulations become very slowly. So the challenge to resolve how you optimize mesh quality. And if you look at real rocks, how you deal again with surface roughness at the scale at the surface, with the roughness of the rock at the pore scale. To do our experiments, we set up a little flow cell so we can inject different fluids, and that is done sort of in collaboration with Eric's group, because they have all the laboratory experimental expertise that we really don't have. So we've set up a flow cell. We can inject two different fluids. You have a camera, high-speed camera that images the fluid flow processes in this little flow cell that holds 3D printed microfluidics. You have an effluent, and you just capture the data, you just capture the video data of the displacement processes. And you've shown that in some first tests that it actually does work. You need to very carefully calibrate your concentration curves for a 3D printed sample so you can extract concentration distributions and compare them to your simulations. We did this for some very idealized pore geometries to begin with. Again, so a lot of homework that you need to do, that we want to do first to get the science right. What Alex is now working on is actually to see how we can eventually get more complex pore structures by changing things like grain sizes, dispersivity, understanding what are the capabilities, the limitations of available 3D printers to print consecutively more complex, more realistic pore structures. We put that pore structure in. Is actually every grain that we're printing exactly 250 micron or 25 micron wide? Do we accidentally start to block pore spaces between individual grains? How do you optimize the 3D printing process so that we can reproduce this, the experiments over and over again in the lab? Continue to improve our validation. So we do our flow experiments with dyes, compare this to the numerical simulation. We have some ways now we can quantitatively extract the amount of mass that was injected through, we can measure the image using image analysis. We can, over time, calculate how much mass is entered our pore geometries and our micromodel. We can compare experimental data with the simulation data. So we continuously build up trust that actually can qualitatively compare the laboratory simulation with the lab experiments with our numerical simulations. And where we're pushing the technology now at the moment is to add particle image velocimetry. So this is Alex here. Very happily working with some collaborators from France, and this Hannah, who helped us to set up that particle image velocimetry. I don't know if you train your eyes, you can just about see. So these are little particles moving through the rock. So what we're doing is we're injecting small particles, 10 microns, small enough that their interactions don't change the viscosity and the density of the fluids. They flow through the pore space. There's a lot of post when we capture the image continuously the movement of the particles. We then use pattern recognition, image analysis, and subtract images from each other to identify clusters of particles as they move. Each camera image has a timestamp, so we can compare then how these these classes of particles have moved from timestamp to timestamp, which tells us what the velocity in the pore space is. So we're getting really quantitative data of velocity distributions at the pore scale. We can again compare it with our simulated field. And there's no one who's sort of going at the moment that level of detail, trying to match experiments, microfluidics, with simulations. Works with single-phase flow. We're now expanding this to two-phase flow. To summarize, my time is coming up there, I believe, and that is really thanks to Rick's vision that he developed a long time ago, that 3D printing will be the next step in how we change our pore-scale imaging and pore-scale modeling work. We did develop an open-source direct numerical simulation tool, pore-scale simulator, that you're all welcome to use, and we're happy to run some short courses for you in the future if you're interested in this. We do have quite a unique lab that allows us to image fluid flow, single-phase, two-phase flow, reactive flow in 3D printed micromodels. We're very carefully, at the moment, trying to advance the 3D printing of micromodels and linking this to numerical simulations step by step. There's a lot of overselling, a lot of hype happening at the moment. We think there's a lot of homework we need to do first until we get to this vision that somewhere in the future, I 3D print my rock with exactly known properties of interest in some very fancy UR process. I know the properties of the rock. I do my experiments. I do my complementary simulations. I really start to understand how relevance, other petrophysical properties evolve as a function of a certain fluid flow process. Do some work with the Aramco Research Center on reactive flow, but that's another 20-minute presentation. If you do want to learn more, go and visit Alexandra's paper. Last quick comment. Here I talk exclusively about natural porous media, rocks, carbonates, plastic rocks. You could energy simulation wants to do simulation for other types of energy, not just hydrocarbons. The same argument that I'm presenting here also holds if you're interested in fuel cells, catalysts. We have engineered porous media. You want to know how fluids move through engineered porous media. You want to understand the displacement process. You want to image them. You want to model them and quantify them. So with that, time is up. Thank you very much. I'm happy to take any questions.
Thank you, Dr. Geiger. Questions? There's a mic at the back, middle of the back room there. Great.
Morning, Sebastian. Great talk. Suleima Karpin from Penn State. On that model geochem foam, you said that you're able to incorporate chemical reactions between the fluids and the solids and the fluids themselves. Does it work in such a way that if you incorporate chemical reactions between the fluids and the solid, it's able to dynamically update wetting properties of the solid in response to those chemical reactions? So you're not imposing.
No. So it's linked at the moment. We've linked it against FreeQC for the chemical reactions. It's written flexibly enough if you want to have another chemical solver, like the gem selector that comes from PSI in Switzerland. You can link it against that one. And we do have wettability alteration models that Shell have published in there that simply tell you, as a function of some surface complexation, some reaction rates, how would wettability change. And we've done some validation of the simulations against the data that Shell published on how the wettability changes. So it has wettability alteration models in there.
Great, thank you.
Okay. No more further questions. Great. Thanks a lot.
Thank you.